Hello everyone. Today, let's talk about how humanity deepened our understanding of light. The book of Genesis records an iconic line, "And God said, let there be light, and there was light." These words mark the beginning of humanity's exploration into light. In ancient Eastern legends, Quafu embarked on an endless journey chasing the sun, striving to hold on to eternal brightness. Our long exploration of light saw clashes between geniuses and centuries of debates, shattering common sense. It even once threw physics into a deep crisis. Today, let's step outside textbooks and retrace humanity's journey of pursuing light. Early human thoughts about light were steeped in philosophy. Back in ancient Greece, Empedocles and Euclid embraced the emission theory. They believed our eyes held a sacred fire. Rays streamed out from our eyes. When these rays swept across objects, we could see the world around us. Soon, doubts arose. If our eyes truly emitted light, why could we see nothing in the dark? Ancient philosophers came up with a clever explanation. Light from our eyes had to blend with sunlight in the air to create vision. This idea sounds absurd today, yet ironically, relying on his profound knowledge of geometry, Euclid derived the law of reflection from this wrong belief. For the first time, humans described light with rigorous mathematics, born from a bizarre starting point. It was the medieval Arab scholar Alhazen who finally disproved the emission theory. In his great work The Book of Optics, he proved the correct intermission theory through precise experiments. Our eyes do not produce light. Instead, we see things because reflected light enters our eyes. His most famous proof was the pinhole camera experiment. He made a tiny hole in the wall of a pitch-black room. Bright outdoor scenery projected clearly onto the white wall inside. Ancient Chinese thinkers also explored light from a unique perspective. In Oracle bone script, the character for light depicts a person with fire blazing above their head. It reflects the simple ancient belief, light comes from fire and the sun. Wang Fu, a scholar of the Eastern Han Dynasty, clearly stated, "Our eyes cannot generate light. Sight relies entirely on illumination from the sun, stars, and flames." Traditional Chinese philosophy divides all things into yin and yang. Yang is closely linked to sunlight. Celestial bodies and flames that emit light belong to pure yang. Shaded places fall under yin. Do not mistake ancient Chinese wisdom for mere speculation. Our ancestors conducted many experiments on light, surprisingly modern in nature. First, light travels in straight lines. Over 2,000 years ago, Mo Jing described this vividly, light travels like flying arrows. They also verified this with the pinhole camera experiment. Rays cross at the small hole, forming inverted images. Second, they studied light reflection. In the same classic text, ancient scholars systematically summarized imaging rules for plane mirrors, concave mirrors, and convex mirrors. Their research led the world at that time. They even speculated that light has a limited range of travel. Based on the ancient cosmic model and shadow measuring methods, scholars calculated, sunlight could only travel 167,000 li. These were scattered observations, not a complete system. Formal optics took shape more than 1,700 years later. The 17th century arrived. The scientific revolution swept across Europe. A legendary debate broke out over the true nature of light. On one side stood Isaac Newton, the giant of science who discovered the law of universal gravitation. On the other side was Christian Huygens, the Dutch physicist and inventor of the pendulum clock. Huygens struck first. In 1690, he published Treatise on Light. He raised a sharp question: if light were made of tiny particles, two crossing beams should collide like billiard balls. In reality, light beams pass through one another with no interference at all. Thus Huygens firmly put forward the wave theory of light. He argued light is a mechanical wave, just like sound. Since waves need a medium to travel, he proposed a mysterious substance called luminiferous ether. This ultra-thin, rigid medium filled the entire universe. Light was ripples moving across the ether. He also established the famous Huygens principle. Every point on a wavefront acts as a new source of spherical waves. The outer edges of these tiny waves form a new wavefront. Light rays run perpendicular to wavefronts. This wave theory perfectly explained reflection and refraction. Let's start with reflection. Imagine a wavefront moving diagonally toward a mirror. Since it strikes at an angle, different parts hit the surface one after another. The leftmost part hits the mirror first and stops moving forward. According to Huygens' principle, this spot becomes a new wave source, sending out circular reflected ripples. The right side is still some distance away, moving onward at its original speed. Light travels at the same speed in this uniform medium. The right side moves forward just as fast as the left side bounces back. When the far right hits the mirror, the left side has formed a large semicircular ripple. The forward distance equals the rebound radius. Connect the outer edges of all these tiny reflected waves, and you get a new reflected wavefront. Rays perpendicular to it are the reflected light. Refraction works similarly. Light slows down when entering water, so the circular waves become smaller. This bends the light path. One key premise lies here: light must travel slower in water. Logically, Huygens' theory was complete and reasonable. Yet Newton stood in his way. In 1704, Newton released his masterpiece Optics. He used a prism to split white sunlight into 7 colors. This proved white light is a mixture of colored lights. He then proposed the corpuscular theory of light. Light is a stream of tiny particles, like bullets fired from a gun. This theory also explained common optical phenomena. Reflection is simple: light particles bounce off mirrors just like ping-pong balls. For refraction, water molecules attract light particles. The pull changes their direction. Newton concluded light travels faster in water. This directly opposed Huygens' view. This difference would become fatal for the corpuscular theory 2 centuries later. In the first round of this great debate, the wave theory matched the corpuscular theory in experiments and logic. But Newton's authority dominated the scientific world back then. Huygens' wave theory was ignored for a full century. The corpuscular theory ruled physics throughout the 18th century. The 19th century came. After 100 years of silence, the wave theory made a powerful comeback. In 1801, Thomas Young conducted one of the most elegant experiments in physics, the double-slit experiment. If light were particles, 2 bright stripes should appear on the screen, just like bullets passing through slits. What Young saw instead was a pattern of alternating bright and dark fringes. This could only be explained by waves. When 2 light waves meet, overlapping crests create brighter light, known as constructive interference. A crest meeting a trough cancels out, forming dark bands, known as destructive interference. The double-slit experiment became an unbreakable barrier for the corpuscular theory. In 1818, the French Academy of Sciences held a competition on light diffraction. A young engineer named Augustin-Jean Fresnel submitted a paper based entirely on wave mechanics. Simeon Poisson, a loyal supporter of Newton, examined Fresnel's equations. He thought he found a ridiculous flaw. According to the formulas, if light shines on an opaque coin, diffracted waves will bend around its edges. A bright spot will appear right at the center of the coin's shadow. Poisson mocked the idea. A bright spot in total darkness? He claimed Fresnel's theory was wrong. François Arago, host of the competition, decided to test it with real experiments. He prepared a small disk and adjusted the light source. The result shocked everyone. A brilliant spot truly appeared in the center of the shadow. The prediction meant to defeat the wave theory became its strongest evidence. To mark this ironic twist of history, physicists playfully named the bright spot the Poisson spot. With this experiment, the wave theory regained full recognition across Europe. Let us recall the old dispute. The corpuscular theory claimed light speeds up in water. The wave theory claimed it slows down. In 1850, Léon Foucault measured the speed of light in water accurately. The result proved light travels slower in water. This final blow ended the century-long dominance of the corpuscular theory. In the 1860s, James Clerk Maxwell revolutionized physics. He unified electricity and magnetism with his famous equations, creating the legendary Maxwell's equations. While calculating the speed of electromagnetic waves, he derived this concise theoretical formula. When calculating the speed of electromagnetic waves, he used two fundamental constants from electromagnetic experiments. The calculated speed matched the measured speed of light exactly, 300 million meters per second. Maxwell drew a firm conclusion: light is nothing but an electromagnetic wave. Light finally cast off the old concept of ether vibration. By the late 19th century, physicists believed the grand building of classical physics was complete. Sound, light, heat, force, electricity, and the secrets of all things in the universe seemed to be written into the ultimate formula for perfect explanation. Then Lord Kelvin raised a concern in a speech. Two dark clouds hovered over the clear sky of classical physics. One cloud was black-body radiation. It would expose the limits of classical physics and usher in quantum mechanics. Scientists tried to explain how hot objects emit light. Classical formulas predicted energy would rise to infinity in the ultraviolet range. This famous puzzle is called the ultraviolet catastrophe. To save classical physics, Max Planck put forward a bold assumption in 1900. Energy is not continuous when emitted or absorbed. It comes in discrete, separate packets. The smallest unit is called a quantum of energy. Its formula is E equals h nu. Here h stands for Planck's constant, and nu stands for light frequency. Planck himself thought this was just a mathematical trick to fit experimental data. He never imagined he had opened the door to the microscopic quantum world. In 1905, Albert Einstein, then a clerk at a patent office, studied the strange photoelectric effect. When light hits certain metal surfaces, electrons are knocked out. The phenomenon follows strange rules. Low-frequency red light cannot eject electrons. No matter how bright or long it shines, electrons stay still. High-frequency ultraviolet light works instantly. Even extremely dim UV light can knock out electrons at once. According to classical electromagnetic theory, energy builds up gradually. Bright red light should accumulate enough energy to free electrons eventually. Einstein adopted Planck's quantum idea and proposed the photon theory. Light is made of individual particles called photons when traveling and interacting with matter. The photoelectric effect now makes perfect sense. A red photon carries low energy. It cannot knock electrons free, just like a ping-pong ball hitting a truck. A UV photon carries high energy. It strikes like a bullet and ejects electrons immediately. For this groundbreaking work, Einstein was awarded the Nobel Prize in Physics in 1921. For 100 years, the corpuscular theory was largely overshadowed by the wave theory. Now it staged an incredible historical revival in the new guise of quantum theory. Light behaves sometimes as a wave, and sometimes as a particle. Physicists were utterly puzzled. In 1924, the French Nobel and physicist Louis de Broglie put forward a groundbreaking idea in his doctoral thesis. He wondered, if light, a wave, has particle traits, could particles like electrons, protons, and even us humans also act as waves? From this insight came the de Broglie wavelength formula. Here, P stands for momentum. This seemingly bizarre yet elegant theory won high praise from Einstein. It was soon fully proven by the electron diffraction experiment. The 3 centuries-long debate between waves and particles finally reached an extraordinary conclusion: wave-particle duality. Light is neither purely a wave nor purely a particle. It shows different properties under different experimental conditions. Many thought this was the end of the story. Yet quantum physics held more surprises. Scientists repeated the double-slit experiment with a new device, a single photon emitter. It released only one photon at a time. Logically, each photon could pass through only one slit. But as more photons accumulated, interference fringes still appeared on the screen. Every single photon passed through both slits at the same time, interfering with itself. Physicists set up detectors beside the slits to observe which path each photon took. The moment the detectors turned on, the interference fringes vanished. Photons behaved like particles, leaving two bright stripes. Switch the detectors off, and the fringes returned. Light seems to know when we are watching. Observed, it acts as a particle. Unobserved, it exists as a wave of probabilities. Later, John Wheeler proposed the delayed choice thought experiment. What if we decide to turn on the detector after the photon has passed through the slits, right before it hits the screen? In 1982, Marlon Scully and Kai Drull designed the quantum eraser experiment. Complete implementation plans were published in 1991. The full experiment was successfully carried out in 2000, known as the delayed choice quantum eraser. The results caused a stir online. Many claimed the future could change the past, and the law of causality was broken. This is actually a misunderstanding. Causality remains unshaken. To understand the experiment, we need a pair of entangled photons, like twin particles. The two photons travel separate paths. The signal photon flies straight to the screen and leaves marks, either interference fringes or two bright bands. The idler photon enters a complex maze of detectors with adjustable mechanisms. Scientists can choose to keep the which path information, which counts as observation. Or they can erase the information, meaning no observation is made. The idler photon travels a longer path. By the time the signal photon lands on the screen, the fate of the idler photon is yet to be decided. It looks as if choices made in the future alter past results on the screen. Here lies the truth. If you stand before the screen, you will only see random scattered spots. No interference fringes exist from the start. The future never rewrites the past. The idler photon's journey creates a set of timestamped data records. Scientists sort the screen marks using these records. Group the signal photons paired with idler photons whose path information was erased. Their marks form clear interference fringes. Group the signal photons paired with idler photons whose path information was kept. Their marks form only two ordinary bright spots. Interference patterns and bright bands were always hidden within the random spots. They are not created by the future, but filtered out by future data. This experiment challenges our common sense about objective reality, not time itself. Before final measurement, a particle has no fixed history or trajectory. We cannot treat photons like flying billiard balls. Before observation, a particle is not a solid object. It is a mist woven from probabilities. The so-called entanglement between future and past is just the overall form of this probabilistic mist across spacetime. Light sets the ultimate speed limit of the universe. It links space and time together. Every breakthrough in understanding light drives huge progress in technology, optical communication, laser medicine, lithography for chips, and future quantum computers. The Bible says God saw that the light was good. To understand light is to understand the logic of the entire universe.